So, now for the moment of truth. We're going to test this thing. To just begin the layout of what's going on here, I made a couple changes since the demonstration of the internal components that I showed you a couple of days ago inside in the lab. One major change was that we are still waiting on the 22S or 90 volt, 350 amp, 30 kilowatt ESC. The mate to this still has not arrived, and because we're not going to be running these fans well above their spec 12S 48 volt rating, what I did to simplify the test and the demonstration is I decided to take off these liquid propane spray nozzles that were originally mounted in front of each of the fans to provide some additional cooling to the motors when we ran them way over spec. Don't be disappointed though. The difference between running this thing at 16S and running this thing at 12S is probably like the difference between an atomic bomb and a hydrogen bomb. It's still really impressive. The other component that I would show you a little change since we were inside is if you take a look at the middle of the engine, you'll see this little collar here, this aluminum or stainless steel collar that's been machined to fit around the inner stainless steel tube and provide a proximal support for the outer jacket that contains the water cooling. The original idea was to provide some gap, some small nozzles or spray gaps to allow a film of water to be sprayed down along the inner tube to keep it cool. But because this is not perfectly round, and this is, we got a very lousy distribution of water as we're flowing back along the tube. So what I did is I relegated this collar simply to a pressure gauge that allows us to measure the pressure within the annular gap between the two tubes, and relocated the water cooling to 4 Yorlock fittings with some very small diameter stainless steel tube that penetrates the outer jacket but not the inner jacket, and sprays water through a small orifice, 0.029 inches. You'll have to do the conversion if you like metric. But at 4 locations, 100 psi water sprays inside, forms a very nice homogeneous mist, and then flows as it turns into steam down the end of the tube. One of the things that you'll also notice, if you look down along the side of the tube here, you'll see that there is a small gap in this 28 gauge sheet metal that's been rolled into a near complete tube. There are 2 of these, and the 2 jackets nest around each other so that the inner and the outer have their gaps 180 degrees apart. And by using the collar clamps to hold this thing tightly into a unified jacket, it's leak-free, it's very adjustable, it's easy to work with. It's a nice idea if you don't want to do some precision machining. But you will notice that the gap here is probably about 1 centimeter or 1.5 centimeters. And if you look all the way down at the other end of the tube here, you'll see that it's come down to about 3 or 4 millimeters. The jacket itself is actually symmetrical, but what we did is we took advantage of these clamps to adjust the gap from a 3 millimeter gap between the inner and the outer tube to a 1 millimeter gap at the very end. As a result, the very large volume of steam that's produced by the heat rockets out the back of the jet around the flame, around the hot air, and adds a few additional newtons of thrust. So we get kind of 2 birds with 1 stone. By adding the water cooling, we get some additional thrust. Now, I'm going to back up here, and I'm just going to run all the way down the engine just to give you an idea of what's going on so you know what all the parts are doing. This is a high voltage spark that generates about 40,000 volts and very high energy pulses. They're sent into a spark gap that is located in the middle of the tube. The entire apparatus is sitting on some linear bearings here that provide a very low resistance, low friction support for the engine. Despite any kind of lateral loads, it stays very well aligned. And countering this position of the slide are these 2 spring balances. We've upgraded from 10-pound spring balances to 10-kilogram spring balances times 2. So you'll be reading on the little insert during our testing the pound scale, which goes up to 20 pounds per balance. So pegged, this engine would be producing about 44 pounds of thrust if we were able to manage to peg it. The fans that we have in here, as before, are the JP Hobby 90 millimeter diameter 12S fans, and the first one is clockwise, the second one is counterclockwise. As a result, we do not need stators between them as you normally do in a turbojet to prevent the vortex, the rotational velocity of the air from each stage, building up a very high speed rotational velocity. The second fan actually benefits from the first fan because they're counter-rotating, so that simplifies this a little bit. As we move back here a little bit, you'll see this feed. This is for the liquid propane. It comes from the tank that we filled in a previous video and sprays the liquid propane through a small nozzle behind the diffusion cone. There's a cone located behind the second fan that accelerates the air as it moves backward and then provides the stagnation area for the additional mixing of fuel and the turbulent blending of the fuel-air mixture to provide a good burn. Here is the tungsten rod, which sticks into the middle of the tube and not quite reaches the center of the inner tube through this alumina insulator. Crosswise at the same location is another tungsten rod which goes completely through the tube and is held by these two collar clamps to keep it in position. This provides a very hot spark about 3 centimeters behind where the liquid propane sprays out. It also becomes yellow hot and remains hot during the burn, helping to ensure continual burning even if we do get some periods when the mixture may be not flammable or we got some trouble. We've got a very hot source to continue to burn even without electrical input. Behind here, this large clamp here, this large collar, that's where the fuel is added. We have 4 Yorlock fittings that again feed very narrow diameter stainless steel tubes that extend nearly to the center of the large burn chamber and support the front or the proximal end of the 50 millimeter by 200 millimeter stainless steel burn tube that contains the mixture as it's being heated and mixed before it blends with the final circumferential air that's moving down here to provide a very, very thorough burn. The end part is held up by 2 tungsten rods that are run through that tube just before its end through small holes to keep it located in the center. It works very well. It's a nice support. You don't see the spacers that are existing between the outer jacket and the inner jacket, but the small stainless steel strips that are welded to the inner tube provide the spacing to make sure this stays concentric and maintains that gap that we want until they end about here and we have the freedom to be able to reduce the diameter of the outer jacket. So that's pretty much the setup here. What we're going to do to start with is I'm going to run the engine without any fuel, water, or any additional components other than the fans so we can get a baseline idea of how much thrust the engine makes when it's just operating electrically. So I'm going to come around over here. I'm going to show you briefly what we've got to drive these fans. In this box here are 2 battery banks, each set up for 12S. If you angle down, you might be able to see on the voltage reading we have 49 volts on each of the 2 channels, and they are turned on, or they're essentially coupled into the ESCs by these large marine 200 amp 200 volt switches. These are a nice source for very high current switches. And in addition, we have a switch here that will power fans that will cool both the ESCs as well as cool the batteries. They can get pretty warm in an enclosed structure. And then finally we have a little 12 volt supply in here that provides some additional voltage for the lighting and other features that we may want to add in the future. Up on top, just a lab power supply to provide a couple of volts to power the water pump that you can see right there. This is just a sort of a lab setup, so we've got a bulky water pump, but this provides the water that cools the burn tube. And then over here we have another lab power supply, and this provides voltage and current to drive the fuel pump, to drive the fuel into the engine. This is just a pulse width modulation control that lets me adjust the speed on the fans so that I can produce whatever kind of output I want by adjusting the pulse width modulation frequency. Interesting thing about this sort of setup is understand this is very bulky. It's bulky primarily because we wanted a very large amount of flexibility at this stage to be able to adjust things. So the positions of burners, the types of voltages we use, the pumps we use. The engine doesn't have to be this bulky, but it's very nice in during the development. Ultimately, we can pack this in a lot more tightly. So the first thing I'm going to do is, if you watch the inset in the video next to me, what you'll do is you'll see a small image of the scale, and as I run the voltage up on here, you'll see what kind of thrust we make when we're just running air. So let's get going. This does get kind of loud. That was full power, maximum setting with the electric flow. The next thing we're going to do is we're going to add some fuel. We'll start with propane. I like to let this warm up for about half a minute to a minute to bring the inner flame tube to red heat. It helps to vaporize the fuel a little bit better. Now we're getting a very dirty burn right now because I'm not running very much air, but that's because I actually want things to get hot. We've got a small amount of water going, but not so much that we're getting very much steam coming out. Once we get to temperature, then what we're going to do is I'm going to add some additional fuel. Interesting thing we found with the fuels is that kerosene, jet fuel, diesel, and gasoline do not burn very well in this engine. Part of the problem is that the traditional flame holder in a turbojet engine has a lot of turbulence that it introduces and produces a very homogeneous burn, helps to vaporize and atomize these lower volatility fuels. The problem with this type of an engine is because we have a low compression ratio from our fans. We can't really afford the back pressure associated with a really good flame holder, and so we have to depend on very hot components and rather linear flow to provide enough distance to get the kind of mixing that we need to burn the fuel. The alcohols, isopropyl and ethanol, worked much better than the gasoline or the other hydrocarbons, but the ethanol and the isopropyl tended to be very sensitive to the air and fuel mixtures, in other words, the fan settings. They would tend to flame out. Methanol is a fantastic fuel for this engine. It has a very high flammability limit. It has a high vapor pressure. It vaporizes very easily. It's relatively inexpensive. And it turns out that it works better than any other fuel in this engine. So what I'm going to do now is I'm going to add a little bit of the methanol, and we'll start getting some flame coming out. Keep an eye on the thrust gauge in the corner of the screen. right, fast forward 1 hour. It's nice and dark. Let me show you what happens when we run this thing at night. Well, I'm very happy with this. This engine has turned out to be everything we expected and worked pretty much as we predicted. By adding the additional fuel, we more than doubled the thrust that the fans alone were able to produce. We generated a very nice sound coming from the engine. It not only produces the high-pitched whine of a turbine, but it also produces a very low-frequency thrumming. It actually vibrates your chest, and it's really neat to watch. In addition, the flame coming out of the end is just priceless. But a number of people, when they commented on our smoke bomb videos, wondered what the police and the neighbors thought about what we were doing. And interestingly enough, while we were filming this video, my neighbor came across the street and asked me how many more times we were going to be running this jet engine. So when we're done here, I'm going to have to go across the street and do a little apologizing. But there are several things that I want to review with this. I would not claim that this engine is superior to an RC turbojet. An RC turbojet is turnkey. You pay your money, and within a couple of hours you've got this installed and you're ready to fly. An RC turbojet is lighter, it's smaller, and in addition, it's much more fuel efficient. We burn about 2 kilograms of fuel per minute with this particular engine. There are a couple of advantages with this engine, though. First of all, to produce about 40 pounds of thrust, you're going to spend about $4,000 on an RC turbojet engine. The two fans, each of the fans from JP Hobby here, cost $250. You're going to have to invest about the same amount of money in batteries to drive these fans, and you're going to need some electronics, the ESCs, some control electronics. You're going to need a few fittings and some hardware. But for about $1,400, you can build an effective jet engine. In addition, unlike the RC turbojet engines, this particular engine does not require refurbishment every 25 hours for bearings. If something breaks, you can fix it, and if even one of the fans blew out, it probably would cost you no more than $250 to just pop a new one in there. The other interesting thing about this type of engine is that because of the very low compression ratio achieved by the two-stage fans, we're comparing this to jet engines in the static mode. When typical turbojet engines are operating, they have a near vacuum in the intake, and so they have to drive at very, very high air speeds before ram effects begin to augment their thrust. This engine, when we reach 250 kilometers per hour, could essentially eliminate one of the stages of the compressor. At 350 kilometers an hour, we wouldn't even need the electric ducted fans. And at that speed or above that speed, you could either choose to take advantage of the additional thrust and efficiency of that additional compression, or you could use smaller, lighter batteries and eliminate the need for the additional weight of the heavy batteries. Furthermore, as you continue to go faster, the fans themselves eventually would overspeed, and there are some ESCs available that have what's called regenerative braking. They can actually pull energy from the motors as if they were generators. The interesting thing about that is that would allow you at very high air speeds to recharge your batteries or minimize the need for your batteries other than for takeoff and landing. But at very high air speeds, an interesting phenomenon may occur, and that's what I want to discuss. For any of you who are not familiar with the way liquid air is manufactured on the commercial scale, typically a very high-powered compressor will compress air to maybe 100 atmospheres, and then they will take that high-pressure, high-temperature air, pass it through an air-to-air heat exchanger, bring the temperature down near ambient, then pass it through a large coil inside of a cryostat. At the bottom of the cryostat, the compressed air is allowed to expand, and when it does so, it cools, and that cool air then passes over those coils, cooling the compressed air further. When that air in turn expands, it cools even more, and that air passes past the coils. That cycle continues until the compressed air is at such a low temperature that when it expands, it liquefies. However, expansion out of a nozzle is not a very effective way of cooling, and so typically what's used is a turbo expander. They allow the compressed air to do work on a turbine to actually extract the energy, and it can be recycled into the compressor. But more importantly, it takes energy out of the compressed air and cools it far more effectively. At very high air speeds, these fans can extract energy from the compressing air that's compressed due to the ram effect. At very high air speeds, these fans could act as turbo coolers, allowing much more effective compression than a typical ramjet is able to achieve at any given airspeed. Subsonic ramjets are not very popular and not known very widely because, first of all, they produce no thrust at static conditions and until they reach relatively high airspeeds. A fan system that allowed you to use a subsonic ramjet at low airspeeds and then at a particularly high airspeed allowed you to compress the air more effectively would allow them to broaden the range over which they become fuel efficient. So that may be an interesting feature of this kind of a jet when we get to very, very high airspeeds. So before I leave you, I'm going to mention three facts. One is, when we get our CNC mill, some of the components that we've manufactured here, we will be producing these in some quantity and providing these through our website so that someone who wants to duplicate what we're doing or improve on it does not necessarily have to go through the machining process. They just need to buy some commercial tubing and do a little metal work, but it would be a relatively easy build. The second thing is that if the people from JP Hobby are watching and are interested in this project, if you're willing to donate maybe 3 of your 120 millimeter fans, we would be willing to build an engine that might produce as much as 100 pounds of thrust. So that'd be a very interesting project. And finally, if there is anybody in the New England area who has access to a wind tunnel, it'd be interesting to test my theory about the turbo intercooling process and whether or not we might actually be able to augment the performance of subsonic ramjets. So in any case, this was a heck of a lot of fun and very loud. What I would ask you to do is to please subscribe, because we've got more videos on the way about jets, not just this kind, but pulse jets and DIY turbojet engines and pulse detonation engines. And we've got videos on other subjects too that we're working on simultaneously. So as I said, please subscribe because it really helps us out. I'll wish you a very good evening. You have a good night.